Okay.
So how long is the presentation and the questions for
30 minutes, and then we have between 10 and 15 minutes for the questions.
Okay.
This is the normal duration of an exam.
Good.
So welcome to this exam. We will see the exam of Ignacio Tampe, Palma, that is opting to the title Informatic Engineering in our university with the work entitled Neural Abstractive Summarization of Online News Discussion Threads. The committee is integrated by Professor Evangelos Milios from Dalhousie University and Marcelo Mendoza, myself, supervisor from the Department of Informatics. Ignacio will have about around 30 minutes to present the work, and then we will have around 10 to 15 minutes for the question part of the exam. So please, Ignacio, you can present your work.
Thank you, Professor. Well, just as Professor Mendoza said, I'm Ignacio Tampe. Today I'm going to present my work, Neural Abstractive Summarization of Online News Discussion Threads. This work was done during last year on an exchange at Dalhousie University. And just as he said, this work was co-supervised by Professor Marcelo Mendoza and Professor Evangelos Milios from that university. So this presentation is going to start with defining a problem. Then we're going to see some related work regarding summarization in social context. Then we'll see objectives and methodology to see then the results that we got and conclude with what we found during this investigation. To start, we see that every minute now internet users post over 500,000 tweets, send like 200 million emails and almost 20 million text messages. This amount of information has exploded over the years and is starting to develop new applications and products and services. Plus, the area of natural language processing has been key during these years to understand all of this information. But digesting all of this data is impossible now for a human to do it, even for a group of humans, because it's over gigabytes of data that any human can't handle. For example, reading through all the reviews and comments of products, on opinions, etc., can become a never-ending task. And if you only read a sample of them, you might become biased. Given that situation, there is a need for automated mechanism to extract meaningful information that becomes relevant to handle these text datasets. But even though social media has been a major source of information during these days and a major source of data for investigation, little has been done to apply summarization over these data sources. Now, summarization, we're focusing on abstractive text summarization. These methods work by creating new sentences. They write down new text, and they have proved to have a great potential of producing high-quality summaries because the models that learn the language to write down these summaries can correctly phrase information, link different parts of the information, which improves readability and relevance. But they do come with a few challenges. First, we have out-of-vocabulary words. This means that these are words that were not seen by the model during training, and that can possibly lead to unknown, like a misunderstanding of what's the topic. Then we have repetition of sentences. A lot of these models tend to fall into repeating the same sentence over and over because it's the most relevant one. And also sometimes the summary is not relevant for the text. The information is not salient enough. But nowadays, the transformer architecture, in particular models such as Google's BERT and GPT, has greatly improved summarization model capabilities. These models can generate results that are almost indistinguishable from human-made summaries, especially on supervised training tasks. Given that situation, most of the studies on this area has been focused particularly on news articles and scientific publications where golden summaries are easily available because we have the lead of the news article as the summary, and in a scientific publication we have the abstract. So it's easy to gather a lot of information from these sources and create models that are able to fully summarize them. But if we see summarization in social contexts, work hasn't been that similar. Mainly has been focused on mixing social aspects to aid the normal summarization task. For example, some work has used the reader comments to aid the summarization in order to produce a summary that is relevant for the reader, but we're still summarizing the news article. And a more recent work used tweets to describe social events by also using a transformer architecture, but they also relied on a supervised task because they had expert human annotators creating these golden summaries for the model to train on. So we have some challenges that involve social media. That's the reason that it's been so hard to tackle these problems. First, we have the issue of obtaining data and also defining what our neural network is going to do. What's the model's task? Some of these challenges include that we don't have clearly defined summaries to use as our ground truth, because that's part of defining the model task. Also, the information is scattered randomly along the thread and it's non-linear. People comment in a chronological order, but we also have replies to comments and replies to those replies. That means that we form almost like a forest of comments that means the information is scattered, and some information can be relevant and some not. That's why we have also we have a colloquial language and typos that are very common in social media, and language models can handle these out of vocabulary words very well, because even changing just one letter for a computer could mean a whole different word, or it might not even understand it. Part of this is we also have topic driftness and topic dependencies. These problems means that we can start talking about a problem, a discussion in a thread, but as the thread goes by, the topic might drift into something different, or it might go to something completely unrelated. And the dependencies are when we have to take into account that replies depend on the source comment that we are replying to. So our general objective for this project was to create a deep learning model able to create summaries of an entire discussion thread based on the most relevant and popular comments according to user interactions under a social context. And we based this in news discussion in Spanish. In particular, we wanted to extend a BERT to transformer architecture to include attention encoding that is able to pay attention to these relevant comments. In order to do so, we modeled an unsupervised task to approach this multi-author, multi-document abstractive summarization problem. Multi-author because we have a lot of people creating comments, and multi-document because each comment is its very own document. Plus, with this work, we also release a novel data set that includes news description, reader comments, interactions, and that it has a lot of information that I'm going to describe briefly. So our architecture for our network, as I said, is a BERT2 transformer that uses Beto. Beto is a BERT model that was trained in Spanish, and a 6-headed transformer decoder based on the paper Attention is All You Need. Then we use an attention model that is based on likes that people give to these comments to promote the most engaging comments to the decoder to generate the summary. Last, our task is split into twofold. First, we generate the article's title, and we choose comments to be generated by the network via weighted random fashion. I'm going to delve into that more later. So for our text encoding, we grab this text, we clean it, we remove, for example, excessive punctuation, tags that are not meant to be there, so we try to keep it as polished as possible, but we leave, for example, stop words because they aid the model to create readable summaries. And we tokenize it using BERT's own software tokenizer, that it splits the words into relevant tokens that the model can learn to create new words out of. And then we pass all this encoding through BERT to get a vector embedding. Then we combine this vector with the attention layer. Our attention layer is designed as such. We take the user likes of these comments and we extend this vector of the amount of comments that the amount of likes, sorry, that every comment has, using the same amount of components as our encoder vector that I mentioned previously. That means that for every token representing every word of this comment, we assign the same value of likes, and we apply to every token in the entire sequence. To calculate this vector, this attention vector, we take the square root of the likes that every comment had received, and we divide it by the maximum value. That way we can cap it up to 1, and then it goes up to 0. And we use the square root to soften up how much these values increase, because if we have a comment with, for example, 100 likes, and then one that the second most popular comment has only 5, it will be almost impossible for this comment to gain attention for the model, because it's going to be decreased very much by the element-wise product that we do, because we take this encoder vector and we use the Hadamard product with the attention to basically decrease, like lower the value of the vector that comprises the comments that are not as relevant, and keep high the values that are relevant. Then all this information is taken by the decoder network to generate the output that we want. And the model task, as I mentioned, is both generating comments that are picked at random during training, but based on how popular they are, plus generating the news article's title. Our idea with generating the title is to ensure that the network pays attention to words that are relevant, that describe the topic, so we don't drift that much from the original discussion. And we encode it as such. First, we put the news title, then we split it with a special token that tells the network to, say, for example, change task, and then the chosen comments, which we try 1 or 3. Finally, to evaluate and train the network, we use categorical cross-entropy loss, and we use beam search algorithm to generate summaries, because it's a better way to approach text generation, as it's basically a Bayesian and probability problem. And this beam search algorithm allows us to explore different possible summaries and choose the best one given some heuristics like lexical diversity, length, etc. Plus, this model also allows to block repeating n-grams. So we try to mitigate the problem of repeating sentences. That is one common problem in abstractive summarization. Our data source comes from EMOL. EMOL is the online version of the Chilean newspaper El Mercurio. We scrapped over almost 150,000 articles that start from April 1st, 2016 up to April 20, 2019. This data includes the news article, the comments, and the likes. And you can see a little picture of the comment box that you see in EMOL. And we focus our work only in the national news category of EMOL. That way we can also aid in reducing the vocabulary, because although it will explode in the amount of words that it has to learn, but it will end up being 41,000 articles for the model to train on. Then to experiment and to test, we tested every single component of our network to see its impact on the results. We tested every model on Compute Canada's Beluga server. It's an HPCC cluster. And we use an Intel Xeon processor, 32 gigabytes of RAM, and 2 NVIDIA Tesla GPUs. We tried all the combinations from enabling or disabling the likes attention layer, asking the network to predict the news title or not, and either predicting 1 or 3 comments at a time. But to validate this task, it wasn't easy. The most usual metric to validate summarization tasks is called Rouge. Rouge basically works by matching the amount of words that appear in both the expected summary and the generated summary. But the thing is, we had no expected summary per se. And Rouge basically works like a longest common subsequence, for example. So we extended Rouge and we applied to different metrics in order to validate our results. First, we started with cross-entropy Rouge. So what we did is that we applied the Rouge score on every comment against the summary. That way, we want to see how much of every comment is present on the summary, and we get a distribution of these comments. Then we compare this distribution with the likes that these comments got, and we wanted to see how much these two distributions match. That's why we use cross entropy, which is not bound to any data distribution. It works directly with the data that we had. And the idea is that the lower the cross entropy, the better, because it means that you can basically summarize it that the lower the value means that there is less difference between these two distributions. But we didn't stop at that. We also took the weighted recall average scores of the comments. We took the recall score of these comments, that is also how much of the comment is present on the summary, and we weighted that score according to how many likes it received, getting a weighted average. That means that we give a higher priority to more popular comments about what Rouge score they got with this recall value. Then, in order to evaluate the topic driftness, we calculated the classic Rouge score between the news title and the generated summary. To also validate our models, we also took two different external benchmarks that are publications that have already proven to surpass state-of-the-art methods and that show other kind of architectures that also compete on this kind of tasks. First, we use an extractive model. Extractive models work differently from abstractive. They basically select sentences that are relevant, more or less like a highlighter. And this model that we use is a pre-trained language model, which is the same as BERT. And it selects sentences based on centroids. So basically, it splits all the comments into different groups and try to select representing comments of those groups to extend coverage and avoid repetition. And also, we use a sequence-to-sequence architecture for our abstractive benchmark that has an attention built in and also uses beam search to generate a summary. Sequence-to-sequence models were the most common way to handle natural language processing tasks before the transformer architecture became the de facto option. This is the results that we got using one comment generation. As I said, the lower the value of cross-entropy Rouge, the better, and the higher the value of recall and the recall on the title, the better as well. In this case, we were surprised to see that the best performing model was the one that had the attention disabled, but it didn't have the title prediction enabled. And we proved this with a t-test with a p-value of less than 0.05. And here's the distribution of these cross-entropy scores. You can see that it's also relevant that, for example, extractive methods and the baseline, that is our transformer model without any addition that we included, had more variance of these results, so they're less reliable. All of our three models with title prediction, attention, and a mix of both had very similar results, but only title prediction had a marginally better result, but it was still statistically significant. When we moved to three comment prediction, things were different. First, well, the scores were better all across the board because we're giving a better chance of the models to select relevant comments. But this time, our attention layer and title prediction enabled both outperform every other model. And we have much higher recall values to compare with. That means this starts proving that our network is working. And here we see the distribution. We can see here that the attention plus title prediction, that is the first box plot, is the shorter one, meaning that it's the most reliable in order to generate these summaries. When we explore some of our examples, we can see what's happening. This is a news title. This is an example that our single comment task network predicted. In magenta, you see comments that were taken by the network to use in the summary, and in yellow, those that were excluded. Plus, we include the likes that each comment received to see how well it performed. Here we can see that comments that had received most likes were all of them included in the summary, and those that were not as relevant were excluded. Plus, we see that it samples pieces of these comments. It doesn't just copy the entire comment and paste it like a selective method. It basically samples what could be important. Plus, it's important to know that the attention layer is disabled on text generation because we wanted to see if the network was able to learn which words, which expressions are more important when generating a summary. It wasn't because if we gave it the attention layer enabled on generation, it will be a much easier task. It will just copy the vectors that had the highest magnitude, and that's it. But here we want to force the network to predict the right words by removing the like attention layer on generation. If we see an example for the three comment task, we see something very similar. Once again, we see that comments that with high amount of likes get added, but sometimes we could say that we get this noise of comments that weren't popular when we got them. But you can still argue that maybe the text was relevant and they could have been popular in the future, like if we gave them time to receive likes, for example. Here, the summary was much longer because we used three comment prediction. So we sample a piece of it because it will be it will fit in a frame properly. Here is an underperforming example. We wanted to see what were how these examples that didn't perform as well worked. And we can see that also it's a bad source text. And that repeated along this group of bad performing results. Here, for example, the thread was much shorter. Text where every comment was shorter as well. And even though, according to our metrics, it failed, it still managed to pick the most popular comment. But what we can see is that it repeated the comment, rephrasing it every time, because it starts like with copying it, then it repeats some words, and you can see that the network is not able to fully handle this short thread. By evaluating all these results, that we split it into quartiles. The first quartile is the best performing one because it has the lower cross entropy root scores against the worst performing one, Q4. We can see some patterns. First off, the model behaves well when the news discussion has lexical richness. There's a lot of different words. The words are properly being used. There is less typos, less colloquial words, and that shorter threads with poor lexical use are much harder to summarize, as the one I showed you before. Also, what is important is that a higher variance of likes distribution can also help the model to perform correctly. In that previous example, only every comment had just one like, and this one has 5. But in the best performing example, we had a much variety of likes. It was a much richer discussion for the model to take advantage of. Concluding with that, we can say that unsupervised summarization, the one that we applied to this problem, allows us to extend the range of these classic techniques to new domains where these golden summaries are not readily available, where text isn't as organized as we can expect in such like a news article, like a story, or like a scientific publication, where most of the work has been put into. Also, Allmother is able to handle the likes attention layer and is able to learn the words that are valuable for it, even surpassing the state-of-the-art methods that we evaluated with. One more thing is that the model was able to learn out of vocabulary words, and it took advantage of these lexically rich conversations. The model was able to piece together names like first names like for a president, for cities, and even dates that they were able to handle because it learned to match all these tokens into new words. For future work, we can see that the model has some limitations that are that should be handled. First off, if we focus only on popularity, we can exclude valid opinions that might be unpopular. They could either be against the publication that they're discussing. Maybe they go against the editor bias of this news article. Plus, including a coverage mechanism can promote the diversity in these comments. For example, if we cluster together opinions that are similar, we can then apply our algorithm here to select popular and to like summarize opinions that are in favor or against this news article. And this work also revealed a lot of Rouge limitations for unsupervised tasks. We could see that we had to extend it and rework some of it in order to fully test our model, because the classic Rouge algorithm would have given an awful results because it wouldn't been able to understand what we were trying to do, what was our model task. Plus, it has some limitations with synonyms as well, or maybe verb tenses. Last but not least, I want to acknowledge that this project was possible thanks to CONICET Fondesit grant and the Emerging Leaders from America program scholarship from EDU Canada that allowed me to visit Dalhousie University and work there for 6 months that extended to a year. And this work has been accepted as a paper for publication at the IntelliSys Conference 2021 in Amsterdam, Netherlands. Thank you so much.
Thank you, Ignacio, for your presentation. A very good presentation. You used it very well the time also. So we will start with the questions from Professor Evangelos Milios. Please, Evangelos.
Thank you. Thank you, Marcelo. Thank you, Ignacio. That was a nice presentation. So what I would like to ask is if you can give an elevator speech for this work. How would you explain the significance of this work to the layperson?
I can see that first I would say that this work is also relevant for elevator pitches kind of situations, because other methods of extracting data from social media, such as topic modeling, are not easily digestible. They can give you a very big result and very detailed, but it's not easy for someone that is not expert in the area to analyze. So if I had to pitch this, I'll say that this model is able to quickly summarize what are the most popular opinions regarding a topic. I will say and in an easily digestible, like short text. This could work for companies, governments. If you want to see the impact of a campaign, for example, for advertisement, even like I mentioned at the beginning, for Amazon reviews, for example, you could see, in general, people say this about our product.
All right. So these are like different applications of your method, but can you like phrase it in a compact way, not enumerating the applications, but giving like the prototypical application that that this method would be useful for?
I think this method is able to comprise discussion threads, extracting popular comments in order to give you a short summary of what's being discussed about a topic. I think that compromises the entire like output of our model.
So in summarization, you typically mention the rate of summarization in terms of size. So the summary is 1/10 of the original size or 1/100th of the original size. So can you give a range of how long the summary is compared to the original data that it summarizes?
I have it right here.
Excellent.
So in best performing summaries, we see that, for example, the length of the thread was around 400 tokens, and the summary was reduced to 80 for single comment. Of course, that if we extend to 3 comments, we get longer summaries, but it's only double the size, and we got a much higher result.
So can you have a guess of how the method would perform if you had a lot longer threads?
Well, there is a limitation with using BERT. That is, a BERT can only take up to 512 tokens. That is all. So you'll have to do like partial summarization of the tokens first, of the thread first, using like a moving window.
Yeah.
That's able, but then there is additional challenges of how this works, because we want to keep the dependency that this is one long thread and not just 512 tokens. Though an extractive method first could take what's probably relevant, comprise it into these 512 tokens, and then write a summary on those.
So you do fit the entire thread in your model, right?
Yes.
And then you generate a single summary out of that.
And just in case the method works, like here's an example of the BERT representation using these different BERT tokens to separate 2 comments in this case. And we can see these with this double hashtag, the subtokens that blend together to create one word. In this case, Argentina.
Yeah. Good. All right. So you mentioned social media.
Yes.
So in your work, you used comments associated with news articles in the newspaper, right?
Yeah.
So how would you summarize social media chatter around, say, a news item?
Do you mean like social media in general, like taking all of information from Twitter, for example?
Yeah. So, for example, you have an event, right? So, and it's described in a news article. Right now, you look at the comments in the online newspaper about this article. Okay, but you could conceivably go to, say, Twitter and look for tweets that are relevant to that event, and then
or even replies to this to the newspaper's Twitter account.
Or
I think the model would work just as well, because we only have to maybe include things like extending the likes attention layer to also include retweets, for example. It's also a way to consider engaging comments in Twitter. But I'll say that as long as we have like a list of comments with their engaging value, that in this case we define with likes, but we can define it with likes plus retweets or only retweets.
Yep.
It could apply the same way. I do consider that maybe Twitter's short length could impact the result of the model, but maybe a big accumulation of tweets will suffice to compensate for this shorter text.
And in that case, your volume would probably be larger, so you would have to do something like what you said earlier, to
to like a window
accommodate
moving.
longer. Yeah, exactly, longer inputs. Yeah,
That's true.
Yeah. All right. Okay. Well, I think I'll stop here and let you ask questions.
Thank you, Evangelos. Ignacio, now it's my turn. I have just a few short questions for you. Please go to the slide 23. Yes.
Here.
Why do you think that the attention gets these improvements in terms of recall? When you use attention, you get these improvements in terms of recall.
Well, as we use a weighted recall, we could expect that this attention layer that promoted these comments to be considered when, because one thing that is important to note, that when we trained the task, the random comment that got chosen was not necessarily the most popular one that had the higher value in the attention layer. So that's why we used a lot of, the same example got seen by the network many times, but every time changing the output. It was more challenging for the network, that's why it took a longer time to train. So I think that this attention layer improved the recall because it taught the network proper expressions and words that are relevant. Because, as I said, this attention layer was disabled when we got the generated summaries. So like it wasn't the element-wise product in the generation that did the improvement in recall, but it was that model able to learn from it. And I think that just by, after all, we subtly highlighted with words, with tokens are relevant, with embeddings are relevant, and those that were not relevant at all, we diminished much more. I'm saying the magnitude of the vector that defined these tokens, right? So I say that by giving these hints, the layer managed to pay attention to what's relevant using the self-attention of the decoder, you see? So after all, my guess is that the difference in magnitude during training allow the attention, the self-attention of the decoder to learn, say, vector directions that are more important for the summarization task.
Okay, you also you mentioned that longer threads tend to be more easy to predict. If you have the spider variance in terms of likes, you can perform better than if you have the likes focusing only in a few comments.
Yeah, but that is also, I think, a bias of our metric, because if we consider this distribution, the ones that have more they have a bigger range of values and more comments, it's easier to measure, and there is a lesser penalty of failing. In this bad performing example, here you'll get here, as this model only copied the last comment, we can see that of course when we evaluated recall on that specific comment, we got a 100% recall. But in the other ones, we got almost 0, because maybe only like the word he was included. And that you could argue that it's a limitation of all of these benchmarks, because you'll get 0, 0, 0, then 5, then we divide it by the amount of likes, and you of course get a lower recall value because it only recalled 1. But lexically, because longer threads usually discuss more on the topic, and we could see that the words being used, the comments, relate more to each other, and having that is easier to recall for the model, because here almost every comment is different from one another. So it's either, if you choose one and you leave the others outside, you will easily get a bad performing summary.
I was also wondering how this metric perform if you have different levels of intersection between the comments. For instance, if you have disjoint comments that are working into different vocabularies, for instance, maybe this metric behaves different as if you have an important level of intersection between the comments.
That's right.
It'll
be easier for the model. Sorry?
So what do you think about this observation? Do you think that there are some bias in the metric in terms of some instances on the testing?
I think that's also more than the metric. It depends on the ability of the network to sample this, because even though we have very different comments that use, say, every word in each comment is different from one another, that you could say it's a very hard summarization task. If the model is able to sample important information of every comment that is more relevant, you could get a medium score, I think. But also evaluating on this popularity does lead to this small bias of recalling information, because we want to see how much of every comment is inside the summary. And forcing the network to include words that are only seen in just one comment at a time does involve, like, you could say it's a complete topic driftness for the network, because we're using different words to refer to different things of the news article. So yeah, you could say it's a small bias, that it's also, I think, something that happens in all of summarization. Like with Rouge in general, if I had said that a guy robbed the store and a person assaulted the shop, we get a Rouge score very low, even though those two sentences mean the same. There is some work that has been done to apply word embeddings to basically match how similar these results are, but as word embeddings are, we also get a small bias, because that depends on how well constructed the vector space is on those embeddings. And it could be, you couldn't get a default benchmark for every model that we test, or every model in the academy, because we have to use the same word embedding in order to test them.
Okay, please go to the slide 30. One of your comments indicate, the first comment indicates that maybe we are focusing in popularity, excluding valid, unpopular opinions. What do you think it is a valid, unpopular opinion?
I'll say that, for example, we get a new law project that has some pros and some things against it. People in favor of the government or that approve this law will discuss it, and we also get the editor bias from our source. Particularly, Imol is a right-wing newspaper. You can see that by having that, we have an echo chamber of people that think alike. So if another person that is against this post, he's not going to get likes from the average reader of this article, of this newspaper, because it goes against the usual editorial bias of it. But it could be a valid critique. It won't be not in a complaint, but criticizing or maybe giving some insights of why something could not be as good as it seems. It could be completely valid, but it's not popular.
So popularity tends to underrepresent minorities.
Yes, and in social media in general, acts as echo chambers of opinions.
Okay, and maybe criteria based on a diversification.
Sorry?
Some type of score based on diversification can work.
I think like maybe like ideas of like clustering these opinions or I'm thinking of unsupervised tasks because that was the source of our project, because problems that like stance detection could easily split comments that are in favor, against, or questioning this article, and then we can get a summary of each of those. But as we see, we have to have this information tagged first, and we weren't able to detect it. But for example, topic modeling could give us different clusters of documents that relate to each other and that may be aligned with different opinions, and we can get a summary of each of those and join it together to one big summary of every group of opinions.
Okay, so I'm ready. Evangelos, do you have time for some questions if you need?
Okay, I have a couple of detailed questions. One is about the box plots that you showed. I think it was page 24.
Here's one, yes.
Yeah. So you said that you ran a statistical significance test.
Yeah.
And you got p-values that were less than 0.05. So what did you compare? Which of the models did you compare?
Every model against each other, basically.
Okay.
So we went, we performed t-tests to do so.
Yeah.
We want to see if the impact of every single attribute, you would say, and how we perform against each other.
So based on these box plots, there is quite a bit of overlap.
Yes.
Of the boxes.
So
right?
that's why I even got surprised that the p-values were as low as they were.
Okay.
But here, the attention plus title prediction, you can see that the median is also lower than those similar box plots.
Yeah.
And that's what I think helps in the score.
But intuitively, I would not guess that the p-value would be that low.
Yeah.
Given the overlap. So I would double check that. My second question has to do about training and testing. So did you keep the data used for testing separate from the training data?
Yes.
Okay.
It was split beforehand. And during training, we allow the model to basically run an overfit, and we save different checkpoints along the steps in order to get the best performing one, to give it the best chance of every model. Because guess that giving the same amount of steps wasn't as fair as just getting the most performing network.
Good, good. And one very last question. So on slide, okay, so slide 6, actually no, slide 8, based on the number of slides, yeah, slide 8, you mentioned nonlinear.
Yes.
So what do you mean information is nonlinear?
Is that we have a chronological order of comments when people arrive and comment, but if we get a reply that, even though it appeared later in the thread, is not linked to the last comment, it's linked to the reply that the comment replied to.
Before, okay. Yeah.
Yeah, that means not linear. You can I see it as a forest because we get these three structures that come from every comment, even though these trees are not very deep. They're only like 3 levels deep in average, but it was enough to be like to take in consideration that that's how social media works. Like if we take it to Twitter, we get this graph of distribution of tweets that are much longer and deep.
Good. All right. Thank you. That's it from me.
Okay.
Thank you.
So thank you, Ignacio. Now we will evaluate your presentation. So, José.
Sí.
¿Cómo procedemos ahora? ¿Tenemos que irnos a una sala distinta o cortamos la transmisión y le pedimos a Ignacio que vaya a una sala
Sí,
distinta?
voy a cortar la transmisión y voy a poner a Ignacio en espera y ustedes pueden discutir.
Ok.
So you're inviting Ignacio back? Oh.
Yes. He's here again. So, Ignacio, it was very easy for us to evaluate your presentation and your manuscript. We think that your work largely exceeds the requirements to achieve the undergraduate level. So we are very close to a master thesis work. we are very happy with your advances, and we congratulate you for your exam and your manuscript. And the qualification is 100, the maximum note in both aspects. So we congratulate you. So you now have the title of informatic engineering.
Thank you.
Congratulations from me too. It was a joy to work with you and host you at Dalhousie.
It was a pleasure as well, even though our stay extended for a little longer. Thank you.
To COVID.
Yeah.
If you want to say some words to the audience, we are in a live streaming.
Yeah. Well, it was quite a work working on this. At first, I was very like, it felt overwhelming to start this project because it was like, wow, texturization, it was all new, and it was quite very rewarding to do it. I was very happy with the work, with all the process of presenting and doing it, and like this whole career that was 6 years of studying. That was hard on times. It was tiring, but I always had family. I always had friends, and that they're waiting to come inside. You can come now. Because they wanted to hug me. I'm very excited to finally like to finish this and do it properly, even though I'm stuck due to quarantine because of a contact for COVID. So we didn't do it in Santiago as I expected. I'm in the south, and well, I'm truly happy. It felt very rewarding to present it, to have it accepted at the conference. It felt like a lot of work, and thank you, Professor Evangelos, for hosting us and keeping us there during the quarantine. It was very generous of your part, and it was being able to use all these this cluster was very cool. It wasn't even possible to do the thesis without it. So thank you, both of you, for guidance, for all the meetings, all the support, and thank you to everyone, friends and family that were always with me together, and to my boyfriend Felipe that also supported me all day long. So that's it. Thank you.
Very good.
Okay, thank you. Thank Ignacio.
Mhm.
I guess that we are ready.
Mhm.
So thank you to the audience for being here. And now you can celebrate with your
Yeah,
people.
it's worth to celebrate. Thank you.
Okay. So thank you, Evangelos. And we will do
Thank you for
again.
giving me the opportunity to join.
See you next. José, estamos listos.
Okay.
Okay. Bye bye.
Bye bye.
Bye-bye.